So thank you, Jonathan, for that wonderful introduction and for making my job as chair for the first session significantly easier. So this is the quantum computing session. My name is Alexandra Moylett. I'm the chair of this session. And so we're going to start off with our first speaker for Bqit 2019, who is Viv Kendon from the University of Durham, talking about continuous time quantum computation.
Find me a microphone.
Yep.
And I think the mic's on. Yes, there we go. And hopefully a clicker that works. Great. It's good to be here. Hopefully I'll keep you all awake for the next 45 minutes of this talk. I'm going to tell you about a somewhat more unconventional way to do quantum computing and give you some details of recent results in this. So first, just a word about my collaborators. This is work that started back about 2012, talking to Sugato at a meeting of the Adiabatic Quantum Computing Conference. We've then got a couple of papers out, one with James Morley, who's a student at the UCL CDT, and one with Adam Callison, who's a student at the Imperial CDT. And Nick Chancellor was my postdoc and is now a UKRI Innovation Fellow at Durham. So that's, I should acknowledge, I am still a Quantum Technologies Fellow under the EPSRC funding program, but not for much longer. July is when I run out. Whoops, that's a little tricky. Right, overview. So I'm going to talk about quantum computing in general, to put this in context. Talk a little bit about discrete and continuous issues, particularly encoding and why that's important for computing. Then about how we use Hamiltonians for processing computing in continuous time. And I'm going to look at the search algorithm and then a spin glass problem to give you. So the search problem will be very familiar. It's Grover's search in a continuous time setting. The spin glasses are a harder problem, and this just to show that it's not just search we can do by these methods. So here's a kind of general statement about what quantum computing is. So we've got some kind of input there. That's the problem you want to solve. You're going to need to encode it into a quantum state. Then we're going to do some processing on it. That U is unitary evolution, or you could do open quantum systems, but in which case you can enlarge the Hilbert space and get it back to unitary, so that's like adding ancillas. You'll get an output state. You'll then need to decode it and get your result. So that U, it can be a gate sequence, so the way everybody's familiar with. Or we might engineer a Hamiltonian so that, and it's a time-dependent one in general, so that if we just run that Hamiltonian on our system, that's just a fancy maths way of writing, evolve it under this Hamiltonian for a period of time while I change the Hamiltonian as well. This is what you tend to do in labs. Actually have to use a Hamiltonian type of evolution. So this picture actually covers a lot of quantum information processing, including communications. And the communications, what you want is your output to be the same as your input. In other words, you're trying to transmit a message over space or time. And doing the identity is actually quite hard when it's separated by some distance or time. So that's not meant to be a trivial statement by any means. I just want to note that encode That encode step has some arbitrary choices in it. I've not got a whole lot more I could say about what encoding and representation is. Not in this talk, we haven't got time. But just to note that if you choose, say, to do spin down as your 0 instead of doing spin up as your 0, it doesn't make a difference so long as your encode and decode are consistent with that. So you have a choice in your physical system about how you choose to make your 0s and 1s. And that's something sort of fairly fundamental to what we mean about encoding and information. So on that subject of encoding, there's some more things that, or issues that are important here. So let's just think about encoding numbers for a minute. So I could encode them by having that many things to represent my number. So I could, so there's 1 to 4 with little black dots. I could also count in binary, and there I'm counting up to 4 in binary. And that doesn't look too different for the first few digits. But if I now go to 8, there's 8. I've had to double my 4, so I've got twice as many there. But if I go from there to there, I've only added 1 more bit. So as we get to much larger numbers, we're going to be much more efficient with our binary encoding than we are with doing a unary encoding here. So I'm going to have log 2 of my number of bits. And when n is large, that's a really big difference. It also makes a difference with the readout. If you've got this kind of encoding, you're trying to do a measurement with n different outcomes. So that might be, if you think of the number of pixels you've got on a CCD camera screen, and you're trying to get the position of 1 pixel in there, that's starting to get pretty tricky for a big number of pixels. But if I've instead got a number that says it's pixel number 17,043, and I've got log 2 of that measurements, each of which has 2 quite distinct, it's either up or it's down measurements to make. So that gives you better for precision because of it's easier to do the yes-no measurements than to have to distinguish all n of them in one go. And it also gives you an exponential gain in the size of the memory. So you've got a reduction, right? Instead of needing n systems, you only need log n of them. It doesn't have to be binary, of course, and there's a good paper about using the resources you've got in a quantum systems back from 2006. But that's just as a backdrop. That doesn't mean that unary encoding is something you never want to use. You might want to transmit small amounts of information in communications, and a unary encoding might be more robust, and it might absolutely be the thing to do. But if you've got large numbers and lots of data, you don't want to give yourself an exponential disadvantage with how you encode it unless you've got a very good reason to. So you have to think about why you want to do this. Now, if I was going to do the standard introduction to gate model quantum computing, I'd be talking about qubits being 2-state systems. I'd give you some examples like electron spin or photon polarization. I'd remind you they're localized, so they're distinguishable, so we're not worrying about Bose or Fermi statistics. I choose a basis. That's the encoding thing, and then you get superpositions, of course. And then I pick up a universal gate set, say Hadamard, C0, and T gates. And I'd add some error correction. And this all sounds like, the way computing works, but with a quantum flavor. But why are we expecting quantum computing to be like digital classical computing? apart from the fact that for a lot of you, that's pretty much all you'll have known in your time. But we have a whole range of models of quantum computing out there. So yes, we have the circuit model, the gate model. We also have measurement-based cluster-state quantum computing. And then that's the binary encoding, digital encoding, and the discrete time processing. You will also then, if you do the Hamiltonian, the continuous time processing, you've got adiabatic quantum computing, quantum walks computing, quantum annealing. There's quantum simulation, which uses all sorts of continuous and discrete processing, the most efficient way to get the simulation you want to do. And then the unary encoding does have variants with continuous variable quantum computing. Now, I think boson sampling sits in this box, but that's debatable because it's debatable partly because we don't necessarily know things boson sampling computes yet. But I think you're doing discrete gates on it with your beam splitters. That's why it needs to sit there. However, that, as I say, it's not important to the talk, but it's something to think about. And then there's a fully continuous quantum analog computing version that goes right back to Seth Lloyd's early papers. So let's have a think a bit more about why quantum might be different. If you've got classical bits, they're either 0 or 1, and you can flip between the two values. That's the basic starting point for classical digital computing. But qubits get to do superpositions. You can change them smoothly between 0 and 1. Now, hence, it makes sense to do discrete gates for bits because bit flip is all you've got. Controlled bit flips, controlled anything else you want to do, sure. But you basically need to flip. Logically, there is nothing other than your 0 and 1 on a bit flip to change it. But for qubits, if you want to do an exact bit flip, it's just as hard as doing other rotations from an experimental point of view. It makes sense to do continuous time evolution for qubits in a way that it doesn't for bits. And this is actually related to work by Lucy and Hardy on looking for 5 reasonable axioms for quantum mechanics, or looking for any number of reasonable axioms for quantum mechanics. But the crucial axiom that made things different was being able to do a continuous transformation between states. If you take that out, you go back to classical. So let's have a closer look at what we've got in this continuous corner here. But notice I'm staying on the discrete, the binary encoding, because I don't want to take a hit on my memory usage by going completely analog. So I think this is an interesting area to look that might be natural for what you want to do with a quantum system. Okay, so how will we encode problems in that setting? We've got our computational basis states. Whoops. So we've got numbers, binary encoded. As I said, I promised I didn't want to give up on that without very good reason. That's the familiar state. That's a superposition of all of the basis states. So that's something you'll have used for all sorts of algorithms. You usually make that by applying a whole bunch of Hadamards to zeros. But you could also apply a transverse field if you've got spins and line everything up in the x direction, and then you'll have that state. So now we want to encode our problem into an n-qubit Hamiltonian, and I'll call it HP. And one way to do that will then be to make the solution the lowest energy state, so the ground state. And then we're trying to find ground states. So for example, if I want to find a Mark state, this is the search problem, then I have make the the state I want to find 1 unit of energy lower than everything else. Yep, that picks it out. I've just made that one state and then 1 unit of energy lower, everything else is the same energy above it. Here's another example. If I've got a term in 3 qubits and I want exactly one of them to be in state 1 and the other 2 to be 0, but I don't mind which. If I put a Hamiltonian term in that looks like that, that will do the job. These are Pauli Z operators, and if one of them is a 1, then you'll cancel, you'll get +1, +1, -1, -1, so that'll be 0. And anything else, and you'll get a larger number here, and when you square it, it'll be a higher energy. So you may not have met stuff like that before, but there are methods to encode classical problems, particularly optimization problems. Think of this as Lagrange multipliers or something like that. To encode a problem into a Hamiltonian without knowing the answer. So you set up, you've got a Hamiltonian, you don't know what its ground state is, but you do know you've put enough constraints on that when you find it, it's the solution to your problem. So in that setting, adiabatic quantum computing works like this. Excuse me. So this was first introduced by Eddie Fahy back in about 2000. I will give you the slides, Andrew, if you want to stop blocking people's view with your mobile phone. We're going to initialize in the ground state of a simpler Hamiltonian. So we'll make that the H0, some kind of H0. That's easy to prepare. So that's the point. You choose something where you know you can make the ground state. And then we'll adiabatically transform from that Hamiltonian into the problem Hamiltonian. And if we do that slow enough, we'll stay in the ground state the whole way. So what's slow enough? It's determined by the adiabatic condition, which depends on the gap between the ground state and excited states. And then this is kind of how fast you're changing the Hamiltonian. If you change it too fast, you'll make transitions. If it's slow enough, you'll stay in the ground state with high probability. So that parameter kind of tells you how likely you are to have stayed in the ground state. So it kind of gives you the success probability. But it also tells you that the computation will take longer if you have to go slower. This is another way to compute in continuous time. Eddie Fahy is also on this paper from 1998. He got around at doing some really good stuff at that point. But Andrew Childs is the person who's best known for developing continuous time quantum computing. So we have an adjacency matrix of some graph, which means you've got ones where there are edges and zeros where there aren't. We can then do a Laplacian where we put some diagonal elements in which are just the degree of the graph. This is not particularly important in our case. Then what we've got is a symmetric matrix. And if it's symmetric, we can make a Hamiltonian out of it, because symmetric is a subset of Hermitian. So we can just make a Hamiltonian minus gamma. Gamma is a hopping rate times the Laplacian. The hopping is hopping along those connected edges. And then a quantum walk is just the Schrödinger equation applied to that, e to the I ht. And then we'll measure after some time t and see where we've got to. Which by itself doesn't sound like it's going to do anything for us, but it does. However, first I need to talk about encoded hypercubes. So these are not quite hypercubes yet, but you can see where the sequence is going. what the hypercube graph has the Hamiltonian. There's the diagonal bit with the degree of the vertex, and then we just have sigma x's, a sum of them. And so we can see how it works on here. Here's my 2 qubits. If I do a sigma x on this one, I'll get to here, so I'll have moved along this edge. If I do a sigma x on the other one, I'll move here, so I've moved along this edge. And you see we've got 4 vertices, 2 qubits to represent it. That's what I mean by encoded. And the sigma x flips 1 bit at a time, and if you've put the labelings in the logical way to do that, you'll move along the edges of the hypercube. So in that sense, I'm going to be mostly talking about quantum walks on that hypercube graph, but it's a virtual hypercube graph. I'm going to label the edges with my qubits, and I've only got little n qubits for a hypercube with big N vertices. So now let's think about the search problem, because it's the problem everybody is familiar with in general, but maybe not in this setting. So there's the Mark state Hamiltonian. It's a little bit inconvenient when it's written in qubit terms, because you have a whole bunch of complicated Z operators. We're going to ignore that for now, because this is in many ways a toy problem. We can solve this analytically. There are also gadgets that we have that can implement this Hamiltonian with some ancillars to second-order imperturbation theory. What's interesting about that is it sets us up with a testbed problem where we can solve it analytically, computationally, and set it up in the actual physical hardware quantum computer you want to test. And then you've got the whole range of things to compare with. 4 large sizes because of the symmetry in the problem. So you can solve it for much larger sizes than the normal sort of 20, 30 qubits you can simulate classically. So now we're going to use that hypercube Hamiltonian for the easy Hamiltonian. The ground state of that is that superposition of all possible states I had up earlier, conveniently. And I'm now going to apply a time evolution where I've now just generally said I'm going to have some amount of the easy Hamiltonian and some amount of my problem Hamiltonian. And then I'm going to run that. I'm going to measure after a suitable time, and we know that's going to be proportional to the square root of n, because we know we get a quadratic speed up for the search problem. And indeed we do. So I've got a picture now for people that prefer pictures to equations, if you've been hanging in there. So there's my 2 time-dependent functions of the easy and the hard Hamiltonian. If I do a quantum walk, that one becomes gamma and that one becomes 1. If I do adiabatic, that becomes 1 minus s, and that becomes s. And this is what it looks like. I think this is probably 8 qubits from James Morley's simulation. So if we do, that's the quantum walk, where we just turn them on and run. And we get Rabi oscillations, basically. That's adiabatic, and it's going pretty monotonically up towards 1. But we could do something in between. You can see I've squished this towards the quantum walk. And now you get something that oscillates, but is still heading upwards. But before we quite get to the interpolation between those two, we need to work out what gamma and the s as a function of t are, because those are crucial for getting the speed up. More maths, but I'm not going to go through it in gory detail. all of the continuous time quantum search algorithms are solved analytically. In the large n limit, they reduce to a two-dimensional subspace, which is just a single qubit. So this is the single avoided crossing model from the paper of reference I'll give in a bit. So there's the 1 minus s, and there's the s, and there's the easy, and there's the hard Hamiltonian, and it turns out to look like this in that setting. Actually, there's more than one way to write it, but this is the simplest one to see. So we're going from state 1, which is the eigenstate of that, to state 0, which is the marked state. We solve the eigensystem for the gap as a function of s, and we get this. And we apply the methods in Roland and Cerf, and we obtain this optimal s of t as the solution of this differential equation. And in the limit where g min is very small, which means the large system size, you end up with a cotangent function here. Solving it on the hypercube looks like that, only a whole lot messier. You don't want to see it. It's in the appendix of the paper if you want to know. So back to the picture again. The quantum walk operates at the position where gamma is a half, which is where s is a half. And then the model reduces to Rabi flops for the quantum walk. So remember, that's what we had here. Only they're going to go up to 1 now, because the fact this isn't 1 is a finite size effect. Now we can see we can interpolate between quantum walks and adiabatic. And this is one way to write a function that interpolates. We've just got a parameter alpha that says how close are we to one or the other. And if you put alpha as 0 or 1 in there, you get back the equations for adiabatic and quantum walk. So this is all in James Morley's work, which is now published in PRA. Oops, let's do that. So now this is my parameter alpha going from quantum walk to adiabatic through all these hybrid algorithms. So I might want to maximize my success probability. So this is just to kind of indicate what we're going to do next, because what I'm really interested in is what happens when you put noise in this. So what happens when you've got an imperfect algorithm or hardware. So what's happening here is you can see the Rabi flops for the quantum walk here. And here you can see it going up smoothly for adiabatic. And then you can see it doing other stuff in between. And then what we're picking up here is the shortest, the highest probability you get for that particular time. And it's not necessarily you've got a sort of hysteresis thing going on here for one of these calculated schedules. So that's telling you is for particular values of the depending on what probability you want for one shot, you're going to need to be able to pick a hybrid algorithm that gives that to you. There's a lot of subtleties though, so I'm not going to go into the details any further. You get to read the paper if you want that. But since in general we won't get success with certainty, we're going to need to repeat the algorithm a few times in order to get a high probability, as close to 1 as you want. Now you've got an initialization and measurement time in there. If you didn't have that, you could just guess repeatedly at 0 cost. So that shows you this is an absolutely crucial physical part of the process, is if you repeat, there's some delay in there, there's some initialization time, which is rolling in measurement as well, that you've got to take into account when you optimize what you're doing. So here we've got the initialization time against the probability that you want to achieve. And you can see that we're changing from 1 repeat to 2 repeats as we get to the point where we can't get that higher probability without a repetition. And it depends on this initialization time, what your best strategy is. So we now have something that is hardware dependent in how you want to run your computation. You can't just do this all in theory. You have to know what your computer is made of that you want to run this on. And we haven't even got to noise or other imperfections yet. Just the fact that you need to repeat runs means you're trading off whether you want to be more adiabatic and run slower versus whether you're better off doing more repeats and taking the hit on how many times you have to reinitialize. Okay, noisy quantum search. I'll power through this a bit faster so as not to lose time for the spin glass stuff at the end. We're going to think of 3 different types of noise or errors. Decoherence on each qubit. So this is just like having high temperature noise, just the stuff you don't want. But then you might also not know exactly what your minimum gap size is, and you might not know where it is exactly. This is more relevant for other kinds of algorithm than this, where you know them analytically, but supposing you didn't know, or supposing you couldn't set the controls in your hardware precisely enough, so you're going to have some error as to you're not exactly where you want to be when you run it. So the decoherence on each qubit, that's easy. It favors quantum walks in the large size limit because they spread faster, and whereas running it, the length of time you have to run for adiabatic, you just basically lose the accuracy due to the decoherence. At intermediate sizes, you do get hybrid algorithms being better. Those details are in the paper. Yep. So for an unknown gap size, you do better with a more adiabatic strategy. Because you need to tune the hopping rate for the quantum walk very precisely, adiabatic is working better now, where you have an error in the size of the gap, because you've got an error in the hopping rate and the quantum walk is not working as well as it could. But the adiabatic finds it even if it's running slower than necessary, so you might not be as efficient as possible, but at least you do find the state. But when you don't know the position, you favor a quantum walk strategy, because now adiabatic is slowing down at the wrong point. So it's failing even though you're running slowly because your slowdown is not in the right place. But the quantum walk just runs, and so provided your hopping rate's good enough, it'll work. So that's a sort of flavor of how having a hybrid strategy can help you, and why thinking of which kind of strategy you want to use, depending on your hardware, could be important. So now let's move on to more realistic problems. So Sherrington-Kirkpatrick spin glasses, these are a classical spin glass. They're frustrated spin systems, and it's NP hard to find the ground state. So for the complexity theorists here, we're expecting a polynomial speedup. We're not looking for exponential speedups here, or anything like that. But they are important because many realistic problems, optimization problems, people want to solve. They are NP hard. Nevertheless, you need solutions to finite-sized examples. As big as you can do, you've got to do the best you can to solve these things. So I'll explain us a bit later why these are quite like typical hard optimization problems. But let's look at the model first. My problem Hamiltonian, which is quantum, so I've encoded my classical spin glass problem into a quantum Hamiltonian. I've got ZZ terms and then single fields on here. which are not in the original model, but it's useful in an adiabatic setting to have break the symmetry with these. And these coefficients are drawn from a Gaussian distribution with mean 0. It's already known that adiabatic can find ground states faster than guessing, so better than guessing. There's the adiabatic version of the Hamiltonian. But nobody had tried quantum walks on them before. I guess nobody thought there was a mechanism that quantum walks could possibly find a ground state like this. But given what I've just shown you for search, it should be obvious that you might at least want to check what they do. We're going to compare with a random energy model where we just make all of the energies of the problem Hamiltonian drawn from a Gaussian distribution. What that means is there's no pairwise correlations in it, which is what makes it like a realistic problem. Real problems have correlations in them. Okay, so if we want to run a quantum walk on this, the first thing we need to do is have a hopping rate. And it mattered a lot that it was very precise for the search. So we're now varying the hopping rate and then just seeing what our success probability is. And you can see we're getting nice broad peaks here out of the spin glass, but we're getting sharp peaks out of the random energy model, which is what you'd also see if you plotted that for search. You'd see a sharp peak. So that's great. It means we've got some leeway in not knowing gamma precisely. And in fact, we can take a heuristic that's just based on the energy scales in the problem and have a good enough gamma. What we now need to think about is when we measure. So that's what it looks like if you run over time. That's how the probability oscillates. So there's no obvious measurement time that you're going to hit. So what we do is we sample at random times, and that's equivalent to sampling from the time average distribution. And the time average distribution of that looks like this. So it settles down at some value somewhere in here. And so long as we measure at different times, we'll average out over happening to measure a peak or happening to measure a trough. We don't want to fix a time and it happened to be worse than average. And the time scaling for that is log m, so it doesn't contribute a significant factor to the scaling, because remember the scaling is going to be something polynomial in n. So this is the log prefactor. And this is what we get. This is for a heuristically chosen gamma based on the energy scales in the problem. So it's not something where we solve the problem to set the hopping rate. And we're sampling over a short time window that's a log scale compared to the size of the problem. So we're doing lots of short runs, and we're getting a low, not a very high success probability, so there'll be lots of repeats. But this black line is what random guessing would give you. So you can see we're definitely doing better than guessing by this strategy. And in fact, we're getting about 0.41. And that's to be compared with 0.5, which is what search would give you. That's the square root. So we're doing slightly better than search with this strategy, which is awesome, right? It works. But we better understand a bit more about why it works. It's not magic, but why is it that quantum walks are managing to do something with this many repeat strategy? So here's part of the story. So this is quite a busy slide. So that blue line is what we had on the previous slide for how well the quantum walk is doing. The three at the top are the random energy model. That's the red one. Which way around? Yeah. it's the Sherrington-Kirkpatrick, it's the spin glass, but now we've put it on a complete graph instead of using the hypercube Hamiltonian driver. And then the green one is where we scrambled the energies. So we took exactly the same energy spectrum, but we scrambled it instead of assigning it to the corners of the hypercube in logical order. So what we've done with these two variants is removed the pairwise correlations. In the first case from the problem, and then the second case because we're now on a complete graph which now has everything connected instead of just the hypercube edges. Now they look like they're doing better, but that's only if you know gamma precisely, which would mean solving the problem first. And without knowing gamma precisely, they're no better than they can't do better than guessing. So that's just to indicate what's going on with the problem. It doesn't actually mean you can solve it any better that way. But then we took our random energy model and we added some pairwise correlations to it. I did this by assigning the energies to a gray code and then resorting it back into normal counting order. Ask me afterwards if you want to understand what we did there. It's not actually a hard problem as defined, but it puts some pairwise correlations into exactly the same energies. And then what you get is something that's behaving much more like the spin glasses. So it's really important that the pairwise correlations in the problem are matched with the hypercube Hamiltonian that is the right thing to be dealing with bit flip updates, if you like. So if you've got a pair of spins, one bit flip of one of them will change you from being satisfied to unsatisfied or vice versa. There's a second reason why, to do with how quantum walks work, that I don't have time to go into in this, and it's not in my slides, don't worry, didn't even try. So that's our picture, this is wrap up now, that's our picture of continuous time quantum computing. Got adiabatic, quantum walk, open system effects on there, pretty much any kind of Hamiltonian evolution, but we don't know which ones are good. There's a huge space of quantum control questions as to what's going to work well. This is because qubits do superpositions and classical bits don't. This is why it makes sense. A note about quantum annealing. It's kind of like a noisy version of adiabatic quantum computing where you're cooling to get to the ground state, but it may also kill coherences, and so you may not get the quantum advantage. It's not clear what that trade-off is. And in the literature, quantum annealing and adiabatic are used interchangeably. The terminology is massively confusing at this point. You have to read the paper to discover what they're actually talking about. There are some limitations, both in scaling. There's evidence that you can't set the Hamiltonian parameters precisely enough at around 2,000 qubits. I don't care for the minute. 2,000 we can do a hell of a lot with. Limits could be higher for other hardware. Verification isn't always an issue. Error correction standard methods don't apply, but there are some techniques out there. So here's my summary with the two papers for more details. So quantum walks find spin glass ground states better than Grover's search can do it if you set yourself up with the right encoding and Hamiltonian. And we've got a fairly unified framework for thinking about hardware and what it might do in a continuous time setting, because this is a natural thing to do with qubits. And the hybrid strategies can work best in realistic hardware. Thank you. Thank you. Microphone's coming.
Hi, thank you for the. Oh, yeah. Hi, thank you for the talk. I was wondering about extensions of what you did. Have you tried to think in the direction of quantum adiabatic optimization algorithms, and whether they could be related to somehow to these hybrid heuristics?
So, you're talking about QAOA?
Yeah.
Yes. Yes, you could perfectly well take any of this and run it in a digital quantum computer as a QAOA algorithm. So so the algorithmic techniques themselves would expand what you can do with that if you have a digital quantum computer, definitely. Yeah.
Thank you very much for the talk. So in the spin glasses thing, I'm not sure I totally understood the problem. Could you explain again what the P infinity was on the y-axis? Like, what is the problem
Okay.
the algorithm trying to find?
Yeah, so the P infinity is a convenient thing to use because you can calculate it from the spectrum of the Hamiltonian. So you just need to diagonalize the Hamiltonian and you can calculate P infinity. So it saves you time in the numerical analysis. So when I had the, go back to that one. So that's got P infinity and this short time one on, and that's where it shows that the fact that I've worked out P infinity has given me a good guide to what I'll get when I only run for short times.
So is the P infinity what you're actually trying to obtain? That's what you want to
It's kind of it's the long time limit that you'd get. So it's kind of a bound on what you get, but it's not really because some of the spikes go above it.
Okay.
Yeah,
Thank you.
but you can see how closely it tracks the short time.
Yeah.
In the interest of time, I think we should move on. So let's thank Viv again.